Hey everyone, and welcome. In this explainer, we're going to do something a little different. We're not just talking theory today, we're actually going to design a lesson together from scratch. We're tackling a classic, Newton's laws of motion, and we're going to build a lesson that really, truly makes it click for students.
Right, because let's be honest, we've all been there. Your students can recite F equals ma, they can plug the numbers into the formula and get the right answer. But the second you ask them to explain what's happening in the real world, that connection just isn't there. So that's the big question, isn't it? How do we get them from just memorizing to actually understanding?
Exactly. And the answer is to kind of flip our whole design process on its head. Instead of starting with a formula, we're going to start with the world around us. We're going to use what's called a three-dimensional learning approach, based on the next generation's science standards, to build a lesson that gets students thinking and, more importantly, acting like real scientists. So you might be hearing this term three-dimensional learning and wondering what it's all about. Well, it's the big idea from the framework for K-12 science education. And really, it's a fundamental shift. It's about moving past teaching science as just a long list of facts to memorize. Instead, we're weaving together the core ideas, the actual practices of science, and those big picture concepts that connect everything. And you know, what I find so powerful about this whole vision is who it's for. This is not just about training the next generation of rocket scientists, though that's great too. It's about creating a whole generation of scientifically literate citizens, people who can think critically and understand the world around them. It's really about science for everyone. Okay, so let's break down these three dimensions. I like to think of them as the knowing, the doing, and the thinking of science. The disciplinary core ideas, or DCIs, that's the knowing. It's the key content, like Newton's laws. Then you've got the practices, that's the doing. It's what scientists actually do, asking questions, building models. And finally, the cross-cutting concepts are the thinking. They're the lenses we use, like cause and effect. The real magic happens when you get all three working together in one lesson. All right, here we go. This is probably the biggest shift in how we approach lesson planning. We are not going to start with a vocabulary list or a formula on the board. Nope. A three-dimensional lesson always starts with a phenomenon. And that's just a fancy word for some kind of observable event from the real world that makes students scratch their heads and ask, wait, why did that happen? So for our lesson on Newton's laws, we need something that is just packed with physics. And honestly, what's more packed with force, motion, and inertia than a car crash? It's dramatic, it's something students can relate to, and it immediately gets them asking questions about safety features like seatbelts and airbags, which it turns out are perfect for exploring all three of Newton's laws. Okay, so we've got our phenomenon. The next step is to create a blueprint for our lesson. We're going to take that car collision and really analyze it, mapping it to each of those three dimensions we talked about. This is so important because it makes sure our lesson is truly integrated and not just a fun activity with a couple of science words thrown in. First up, the disciplinary core ideas, the DCIs. As physics teachers, this is our home turf, right? This is the core content. For our car crash lesson, we're targeting the DCI called PS2, which is all about motion, stability, forces, and interactions. This is where Newton's first, second, and third laws all live. It's where we get specific about the knowledge students need to gain. Next, let's think about the doing. What are the science and engineering practices, the SEPs, that our students will actually be doing to figure this all out? Are they going to be developing a model to explain how an airbag works? Or maybe engaging in an argument, using evidence about why seatbelts are so effective? This dimension is all about getting them actively involved in the investigation. And last but not least, the cross-cutting concepts, or CCCs. Think of these as the big themes that connect all of science. They're like mental filing folders that help students organize their thinking. For a car crash, the idea of cause and effect is just massive. The collision is the cause, the sudden change in motion is the effect. Systems and system models is another great one, as we get them thinking about the car and the passenger as an interconnected system. And here on this slide, you can see how it all comes together. This is our blueprint. We've got our one single phenomenon, the vehicle collision, and it lets us weave in all three dimensions perfectly. The DCI, Newton's laws, explains the forces. The SEP has students actively modeling how safety features work, and the CCC has them using cause and effect to structure their entire explanation. See? It's a completely cohesive plan. So we have our blueprint. We know what we want to teach. Now we move on to the how. Step 3 is all about crafting the lesson's storyline. And I want to be clear, this isn't just a list of activities you're going to do. It's a carefully planned out narrative that guides students from their initial curiosity all the way to a deep, evidence-based understanding of the physics. And that storyline should be built around this one simple, powerful idea from the framework. Kids are natural investigators. They are born curious. Our job isn't to just give them answers. Our job is to create a path that lets them investigate, to let them grapple with new ideas, test out their theories, and build their own understanding. We're not the stage on the stage. We're the guide on the side. So let's talk sequence, because the order is everything. First, you need that hook. You show a crash test video, and the whole point is to get students asking real questions. Not just, what are we doing today? But, whoa, how does an airbag inflate that fast? Or why does the dummy fly forward? Their curiosity is what's going to drive the whole lesson. Then you let them investigate. You give them carts and ramps and sensors and let them get their hands dirty exploring those very questions. They're collecting their own data, discovering for themselves that a bigger force makes a bigger change in motion. They're building the concepts from the ground up. And here's the crucial part. It's only after they've done this that we step in with targeted instruction. This isn't a random lecture. We're giving them the formal language, words like inertia, F equals ma, action reaction, to describe what they've already seen and experienced. And finally, we bring it full circle. They apply all this new knowledge, go back to that initial phenomenon, and now they can build a model that explains exactly how a seatbelt and an airbag work to save a life. That is the complete sense-making journey.
Okay, so we've designed this awesome three-dimensional lesson. We've taught it. But how do we know if students really got it? Well, our assessment has to be three-dimensional too. It just has to. We can't ask them to think and act like scientists for a whole unit and then just give them a multiple-choice quiz on definitions. The assessment has to measure their ability to apply all that integrated knowledge.
And this slide just nails the difference. Look at the left side. That's a classic physics problem. It's not bad, but it only really checks if a student can plug numbers into the F equals ma formula. Now look at the right. That is a true 3D performance task. To answer it, a student has to use the DCI, Newton's laws, engage in an SCP developing a model, and apply a CCC cause and effect to explain a real thing. This is how you find out what they really understand.
So we've just walked through the whole process, from finding a phenomenon all the way to assessing for understanding. The goal today wasn't to hand you a ready-made lesson, but to give you a new way of thinking, a framework you can use to take any topic you teach and turn it into an exciting, real-world investigation for your students.
And here it is, all boiled down into a simple checklist. Number 1, start with the why. Find a compelling phenomenon that will hook your students. 2, build your blueprint. Connects that phenomenon to the knowing, the doing, and the thinking of science. 3, craft that logical storyline, moving from curiosity to explanation. And 4, assess what really matters by designing a task that puts all 3 dimensions into play. And that brings us to the end of our little design session. You know, we used a car crash, but the possibilities are just endless. It could be a rocket launch, a game of tug-of-war, even just dropping a coffee filter. So we'll leave you with this to think about. What everyday phenomenon will you use to bring the laws of motion to life for your students? Thanks so much for designing with us today.